In this video, we will be talking about discrete random variables and probability distributions. This information can be found in Chapter 3 of your book. Random variables are functions, generally represented by an uppercase letter, normally x, whose domain is the sample space and whose range is a set of real numbers. Random variables, or RVs as they're commonly abbreviated, can be discrete or continuous. We'll be focusing on discrete random variables in this video, as well as common probability distributions for discrete random variables. So a discrete random variable is a variable whose values consist of a finite set, either something like 4, 5, 6, 7, 8, where that's a finite set of 5 numbers, or an infinite sequence with a first value, a second value, etc., a count. And while this can go on for quite a while, obviously they're defined values. You can't have decimal points or anything, so they're still integers, 0, 1, 2, and so on. A special case of discrete random variables are Bernoulli random variables, where the only possible values for x, or the random variable, is 0 or 1. And we'll discuss this later when talking about the binomial distribution. When analyzing discrete random variables or conducting experiments with them, each possible outcome has a probability assigned to it, the likelihood that that outcome will occur. The probability mass function, or PMF, displays the outcomes and their respective probabilities of being observed during an experiment. All PMFs require two things. First, that the probability of the outcomes must be greater than or equal to 0 for each outcome, which just states that you can't have a negative probability of occurrence, which wouldn't make sense mathematically. A probability of an outcome being 0 would just mean that it's unlikely you would see that outcome during the experiment. The second thing required is that all probabilities in a PMF must sum to 1, which means that you must observe one of the possible outcomes, and generally only one. A standard PMF problem you might see in class or homework could look something like this. I'm trying to decide between 5 different types of cereal. They are given promotion where there may be between 0 and 2 prizes per box of cereal. Since I'm sticking to a budget, I can only buy 1 box. I want to maximize my chances of receiving prizes. So I look at the data, and the first type of cereal has an average of 2 prizes per box. The second and third brands have an average of 1 prize per box. The fourth type has an average of 0 prizes per box, and the fifth type has an average of 2 prizes per box. So first, let's take this information and put it in table form, which makes it easier to think about. So we have the type of cereal and the number of prizes on average. And we have 5 different types of cereals, and there are 3 possible outcomes. 0 prizes in a box, 1 prize in a box, or 2 prizes in a box. And looking at the data, we can fill in the table like so. Now, to turn this into a PMF, we'll look at the fact that there are 5 equally likely events up here, boxes of cereal that I'll choose, and 3 possible outcomes here. So we'll need to calculate the probability of each of these possible outcomes of these events. First, the probability that I receive no prizes in a box of cereal. The probability of the random variable equals 0. And this will only happen if I pick box 4. That's the only time 0 occurs in our table, which is 1 out of 5 possibilities, which is 20% chance that I'll receive no prize in my box of cereal. Now, for receiving 1 prize, that happens when x is equal to 1, or when I pick boxes 2 or 3 is most likely. 2 of the 5 events have this as a possible outcome, which gives us a 40% chance that I'll receive 1 prize. And the probability that I receive 2 prizes in my box of cereal will occur if I pick box 1 or 5, which is again 2 out of 5, and a 40% chance. And this makes up our PMF, which we can display in the standard form, which looks something like this. Now we can calculate the CDF from the PMF we found in the previous example, Next, we'll look at the cumulative distribution function, or CDF. This function is similar to the PMF, only the CDF shows the probability that the discrete random variable, capital X, will be at most little x, which is stated in the function here. You can derive the CDF from the PDF or vice versa. We will calculate the CDF from the PMF we found in the previous example. Left up here for us to reference. As we mentioned, the CDF shows the probability that large x, our random variable, is less than or equal to little x, the value, and that gives us the probability. So here, we'll calculate probabilities of big X being less than or equal to our 3 outcomes. 0, 1, and 2. So the probability that X is less than or equal to 0 in this case is just going to be a probability that X is equal to 0, because there are no possible values of X that are less than 0. So that probability is just equal to our 20% from before. The probability that X is less than or equal to 1 will be the probability that X is 0, or the probability that X is 1, because that includes the 2 possible outcomes where the random variable X is less than or equal to 1. So we'll sum those to get 0.6, or 60%. And the probability that our random variable X is less than or equal to 2 includes all the possible values of our random variable. So we will sum, in this case, the 3 values from our PDF. To get 1. And the CDF can be displayed in a similar format to the PDF. Obviously, this becomes a bit more useful if there are more possible outcomes, and we would repeat the process here more times before arriving at the probability of 1 for this outcome. Using these functions, we can calculate descriptive statistics about the population. Using the PMF, it is possible to get the expected value, or average, using this equation in bold. In cases where you want to find the expected value, but the random variable is a linear function, such as ax plus b, where x is your random variable, your discrete random variable, and a and b are constants, you can apply these 2 rules to find the expected value. When a is a constant, the expected value of a times x, the random variable, is equal to a multiplied by the expected value of x. And when b is a constant, the expected value of the random variable x plus b is equal to the expected value of x plus b. Therefore, the expected value of the linear equation ax plus b would be equal to the constant a multiplied by the expected value added to b. However, expected value can only tell us where the population is centered. but it's just as important to know the spread of the data as well, which we can calculate using the variance equation seen here on top. Variance is also denoted as sigma squared of x, which hopefully you'll recognize from the standard deviation equation seen below, where standard deviation is sigma equal to the square root of the variance. Now we can calculate all three quantities, expected value, variance, and standard deviation for the previous example. I've left the PMF up here for us to reference in our calculations. We'll start with the expected value. In this case, we will take the probability of an outcome occurring multiplied by what that outcome is. In this case, 0.2 is our probability that we get 0 prizes. And we will go down here, continuing to sum these. And this will give us an expected value of 1.2. Note that this is not an actual possible value for our random variable x, but as we can note that this is not an actual possible value for our random variable x, as we only have the possible values of 0, 1, or 2, but it shows us that the average number of prizes per box is about 1.2, and we can expect to get somewhere in there from a box of 0. Next, we'll calculate the variance. And remember that this formula is the expected value of the random variable squared minus the expected value quantity squared. And that will give something to this effect. So you can see here I've pulled the 1.2 from our previous calculation of expected value, and then I've squared inside this expected value calculation the values of the random variable x. Now, we'll expand this out to get our variance. And see the number of, and you see the value of 0.56 is our variance. And this will directly lead to our standard deviation. Seven, 0.75. Now remember, we've been talking about the discrete random variables only, and I'd like to cover some common distributions for discrete random variables that you'll see often in class and in homeworks. The first of which is the binomial distribution. It has 4 conditions. First, the experiment consists of a series of n smaller experiments called trials, where n is a fixed number beforehand. This means there are no run until experiments where you would continue to run trials until you reach a certain outcome or milestone. That does not apply in the binomial distribution. The second condition is that each trial can have one of 2 possible outcomes. Normally this will be called success or failure, but if you see the words yes or no, heads or tails, etc., that also applies here. Third, the trials are independent of each other. This means that the outcome of one does not have an effect on the outcome of the next trial. And fourth, the probability of success, P, is consistent from trial to trial. And this probability, as you can see, is denoted by a lowercase p. If an experiment satisfies these four things, it can be analyzed as a binomial experiment. A binomial PMF is denoted using the two parameters n and p mentioned in the conditions, where n is the number of trials and p is the probability of the success outcome. Note that you'll want to make sure you know which outcome is called the success outcome. Sometimes this could just be a heads or tails, which isn't always clear as what's a success and what's a failure, so be sure to read your problem statement carefully. And if the PMF is equal to n choose x, x being the number of successes you want to look for in the problem, multiplied by the probability of success to the x power, multiplied by 1 minus p, to the n minus x power. And what's really useful about the binomial distribution is the formulas for expected value, variance, and standard deviation are much simpler, as you can see here. The expected value is equal to n times p, the variance is n times p times q, where q is equal to 1 minus p, and the standard deviation is the square root of n pq. This makes evaluating a binomial function much faster than using the general summation formulas we covered earlier. Another common distribution for discrete random variables is the Poisson probability distribution. A discrete random variable can be classified as following a Poisson distribution if the PMF of x is equal to this equation here. E raised to the negative lambda multiplied by lambda to the x power, all divided by x factorial, and where lambda is a rate per unit time or area. So if you see the words Poisson or lambda, or any sort of rate in a problem statement, you should immediately think, could this be a Poisson distribution problem? The Poisson distribution can be a special case of the binomial distribution if n is large and p is small. Generally, this means that n must be greater than 50 and n multiplied by p must be less than 5. The PMF of this would be represented as shown here, where your binomial PMF can be approximated as a Poisson process with rate lambda, where lambda is equal to n times p. If a question asks about a Poisson process event, or to find the probability of a certain number of events during a time interval, you will need to use this formula shown in bold, where p sub k of t is equal to the probability that k events occur in time t, where alpha multiplied by t is the expected number of events during the time interval t, and this alpha multiplied by t quantity is equal to the rate lambda from the Poisson probability distribution. An example of a Poisson process problem may look something like this. Let's say that I'm very busy and receive on average 10 emails an hour. What is the probability that I receive 7 emails in 30 minutes? Let x equal the number of emails received in a half hour. So I've written the Poisson process formula up here for us to reference. And let's start by listing out the variables we see in this formula and the quantities they correspond to from our problem statement. So we'll start with k, and that's going to be 7, because that's the quantity we want to find the probability of. The probability that we receive 7 emails in 30 minutes, which is our time. However, because our rate is in hours and this is in minutes, we're going to want to convert this to 0.5 hours. Said our rate is the 10 emails per hour, and as e is a fixed mathematical quantity, we can now plug these numbers into our formula, and so we'll have the probability that we get 7 emails in half an hour. Should be 5. And we have e to the negative 10 times 0.5 multiplied by 10 to multiplied by 0.5 to the 7th power, all over 7 factorial. And if you've forgotten or don't remember what it was for factorial is, it is simply, in this case, 7 times 6 times 5 times 4 times 3 times 2 times 1. And it calculates out to 5,040. So, work this calculation out further, you can see that our probability eventually becomes 0.1, or 10% is the probability that I get 70 miles in half an hour. The material we covered in this video comes from Chapter 3 of your book, Probability and Statistics for Engineering and the Sciences, by J. DeVore. If you need more practice problems or examples, please feel free to go look through Chapter 3